Okay, so we've been talking about percent composition, and I believe, let me back this up just a tiny little bit. Yeah, so this was kind of in the notes, and we did this one, I think, together in class, and we applied this to the same logic of your bubblegum lab when you were trying to calculate the percent of sugar that had either left the gum or was still present in the gum. So, and of course we did that by the change in the mass, but we had to know what the whole was when we were looking at the percent composition of this. Now, we're going to apply this to a situation where we're working backwards, and this is going to be leading us up to something called an empirical formula, and that is just a smallest whole number ratio. So, but it's got to be whole numbers. This can't be fractions. Because it's kind of defining or giving us an idea of what the subscripts are for a compound. So let's take a look at this example. We got phenol. It's a compound that contains 76.57% carbon, 6.43% hydrogen, and I believe, let me see if I can roll this. Yeah, so 17.0% oxygen. And they want us to kind of figure out what the whole number ratios are. In other words, what are those subscripts? So we're going to treat our percentages as if they were grams because, and this is how beautiful this works out, if you added all these up, of course you get 100%. Well, why don't we just assume there's 100 grams? So I'm going to go ahead and do that for each one of our elements, and I'm going to convert them into moles because by now you have probably figured out that your mole is your go-to guy. So we're going to say 6.43 grams of hydrogen. And then there's his mass. Excuse me. 17.0 grams of oxygen. Okay, so sorry, I'm sounding kind of far away. I'm looking for my calculator. All right, so let's go ahead and divide. So say 76.57% divided by 12.01, and I get 6.380302. Now, I'm using several numbers with this because, as we have seen, if you round up, this can mess up data just a tiny little bit. It can throw your numbers off. So anytime I do these empirical formula problems, I always try to use at least 5 numbers past the decimal. So it's just good practice. All right, so 6.43 divided by 1.008, and I get 6.3789683 moles. And then I get 17.0 divided by 15.998, and I get a whopping 1.06263 moles. And of course this is carbon, hydrogen, and oxygen. Okay, so now we need the smallest whole number ratio. So I'm going to divide each one of my mole amounts by the smallest number. And because if I didn't, I would end up with a fraction. So I'm going to say 1.06263, and that gets rid of my moles. I'm going to divide this one by the smallest number as well. And that gets rid of these moles. And of course I divide the last one, 1.062633 moles. And that equals 1. Alright, and when I divided this number, I think you get something like 5.998 something. So I'm going to go ahead and round that up to 6 because that's a very sexy whole number. And then I've got 6 for this one. So the empirical formula for this compound phenol is C6H6O. Let's take a look at another one. I think there's no. I've saved this one for. I've saved this one for the warm up tomorrow. So let me insert a page. Okay, so I've got my page inserted, and I'm going to take a look at a sample problem. This one is not inside your notes, so you may have to look. Somewhere else. But let's take a look at caffeine because today in class I just kind of gave them different problems to do. And so I'm going to give you the percentages. And then I want you to pause the video or the lecture. I want you to pause the recording. And I want you to try to do it on your own and work it the same way that we did the one before. And then I want you to come back and I'll have it all worked out for you so that you can see it. Okay. Yeah, so that you can see it in its totality. All right, so here we have 49.5% carbon, 5.15% hydrogen, 28.9% nitrogen, and 16.5% oxygen. And you're going to be working backwards, and you're calculating the empirical formula of a compound called caffeine. So here we go. So go ahead and press pause now, and try to work this problem on your own. Okay, so you've probably worked the problem all the way out, and so what I decided to do was maybe just kind of show like the first part, and then maybe kind of talk about and work out step by step the last part of it, because I feel pretty confident that you're getting the mole and using molar mass as we see in these examples here. So getting to the mole is going to make your life a lot easier. Okay, so and I've been kind of lazy. I haven't written the units here, but let me go ahead and do that now. So these are the moles of carbon, hydrogen, nitrogen, and oxygen. And so I need to get the smallest or the lowest whole number ratio. So I'm going to divide each one of these moles by the lowest number. And of course, that ends up being the 1.03189. So I'm going to go ahead and do that. I'm going to write these in. All right, so I need the lowest whole number ratio. So I'm going to divide by the lowest number. All right, so there we go. And then beautifully, my units cancel, and I end up with a dimensionless number because the number is representing the total number of atoms in the compound, so it doesn't need to have a dimension. Now, when I divide these numbers out, I get 4 for carbon, and I got really close to 5, and for this one I got 2, and of course I got 1 for this one. So the formula for this compound is C4H5N2O1. Okay? Now, this may or may not be your empirical formula, your molecular formula. Okay? So there's an added step when working these problems to calculate molecular formulas. And I want to take a look at those, take a look at one of those right now. We're going to work with one that's really easy and it's really simple for you to see. Okay? Okay, my annotations, maybe. Okay. So let's take a look at styrene. Okay, so this is styrene. All right, so styrene, registered trademark. And I got 92.3% carbon, and I think I have 7.7% hydrogen. And you'll notice again that if you add these together, you get 100%. We're going to treat the percentages as if they are grams. So I'm going to go ahead and do that now. Sorry, I'm not having trouble talking and writing and calculating at the same time. Okay, so here we go. So we got everything to moles, and I ended up with 7.68526, and then I think some other change, and then I ended up with 7.638889 moles for this one. And then, of course, we have to divide by the smallest number, and that happens to be this one. So I'm dividing by the smallest number. And you can clearly see that it's going to be 1 to 1. Okay? Moles cancel, a 1 and a 1. So the empirical formula, and I'm going to call her the EF, equals CH. Okay? So this is a 1-to-1 ratio. I mean, clearly, this is not the molecular formula. Well, it goes on in the problem to tell me that the molar mass is 104 grams per mole. Okay? And I'm going to use that to calculate the molecular formula. So I'm going to write the molecular formula, because that is ultimately what I am trying to solve here. Okay, so that's what we're kind of looking for, because I can clearly see that this is not the case. That is not the molecular formula. All right, so first things first is we need to calculate the empirical formula mass, and of course it's 12.01 and then 1.008, and we get 13.018 grams per mole. Okay? Now, I'm going to take this number right here, and I'm going to say 104 grams per mole. I'm putting the larger number on top, and I'm going to put my smaller number on the bottom because I need a whole number. And you know, if you flip it around the other way, you're going to get a fraction. So, okay. All right, and these, of course, it's a dimensionless number. And when I say 104 divided by 13.018, I get 8. Okay, so when you work the magic, you get 8. So what that means is I'm going to multiply everything in the empirical formula right here, the CH. Remember, this is what we did from here. I'm going to multiply everything by the 8. So the formula for styrene is CH8. That is her molecular formula. So it's pretty cool. So we get to see how we can take percent composition. We can use those percentages to calculate the empirical formula to give us a lowest whole number ratio of atoms. And then I can take the empirical formula, given the molecular mass, of course, and I can figure out what the exact number of atoms are. Now tomorrow, we're gonna work with another example, and we're gonna look at another approach to this, and then we're gonna be getting into balanced chemical equations and how stoichiometry fits into that.